Okay, let's get started. We got into the beginnings of a whole new subject last time, and it was a subject that this Danish professor of physics, Ørsted, stumbled on during a class demonstration. Right now, you remember. For years, he had suspected there was some connection between electricity and magnetism. But the way he had tried to, he'd had ideas on what that connection was. And the specific ideas he had on how the relationship of electricity and magnetism worked actually prevented him from discovering it, because he was using really thin wires, and so there wasn't much electric current, and he was putting his wires in the wrong direction to deflect the compass needle. So he at first didn't get any results, and then suddenly by accident he had it set up right during this classroom demonstration, and he sees the magnetic compass needle deflect when he turns on the current. Now, just to remind you how he had it set up, he he actually had his wire carrying the current stretched over the compass in the north-south direction, and then when he turned on the current, the compass needle would suddenly deflect somewhat off to the west in this particular case. Now, he found that if he picked up the compass needle and put it over the current carrying wire instead of beneath it, then the compass needle would flip in the other direction. It would flip toward the east. Now, the other way he could get the deflection of the compass needle to change is if he leaves the compass below the wire and he reverses the direction of the current in the wire. He tried that too. So let's say he originally had it going in the north direction, the current through the wire. Well, let's say he reverses his battery connections, and so the current's going in the other direction. Then he finds that the compass needle deflects toward the east instead. So it depends on the direction of the current. Troy.
And if you just had static electricity, like just sitting in it, if it was an insulator, would it just not move at all? Or
Right. If he just had a wire or a charged up pipe or whatever, a tube of glass hanging over this compass needle, it wouldn't do anything. See, this is why I've called today's class electrodynamics. All this time up through Coulomb, we've been studying the subject that's now called electrostatics, okay, which means the electricity is just sitting there. Okay, it's stationary. We rub things together and we get, a net amount of electricity on them, just sitting on them. But now because Volta invented this battery, now scientists have a way of generating continuously moving electricity. And they can start discovering the effects of moving electricity, which turn out to be a lot different than static electricity. Brand new things come up when you get that electricity moving. Okay. Now, so what's going on here? What has Ørsted discovered? He's discovered that somehow, when you get electricity moving, when you have a continuous current of it, it exerts a force on a magnet. right? Because that's what this compass needle is. It's just a magnet. It's deflecting that magnet. Now, if a moving current exerts a force on a magnet, do you think a magnet will exert a force on a current? So you're nodding your head. Why?
Well, because if they're connected, then it should do something to it. Like if the magnet was a lot more powerful than the current, maybe it would make it move away.
Make it move, make the current, make the wire move. Yeah, well, that's a natural thing to try. And the reason that's a natural thing to try is because of something Newton said. Evan.
Because if the current exerts a force on the magnet, Newton's third law says that the magnet then has to be exerting a force on the current.
Exactly. One of the things that Newton said was that, in effect, there aren't one-way forces. If object A exerts a force on object B, then object B is exerting a force back on object A. All forces in nature are interactions between bodies, and they're exerting forces on each other. Okay, so the next thing that Ørsted tried, well, let's just get organized here. Okay, so we're continuing Ørsted here, and let's say experiment 1 was he discovers that an electric current exerts a force on a magnet. And also, I mean, that this force seems to have this peculiar direction, that it doesn't exert the force along the direction of the current, but in a perpendicular direction to the current, which struck Ørsted as a little bit odd, but that's obviously what's going on given the results of his experiment. Okay, now, his next question that comes to Ørsted's mind, given what he knows from Newton's third law about forces being equal and opposite between bodies, he goes on to the next experiment and asks, does a magnet exert a force back on the electric current? Now, how would you test that? What's the basic, what kind of a setup do you need?
Can you have an electric, can you have a wire that has electric current moving through it freely and bring that magnet, bring like a magnet or two magnets up to it and see if it has any effect?
Yeah, I mean, what you want is, say, obviously you want to use a stronger magnet than he had in this first case. I mean, these little magnetic compass needles aren't very strong magnets, right? So you want a strong magnet, and you want a setup where the wire that's carrying the current can move easily. Okay, you need those two things. If you got those two things, it should be an easy experiment to easy idea to test. Troy.
Like to have the wire move freely, would he have like a torsion balance or?
Well, I think what he did was, I don't know the details here, but let's, I'll give you the basic idea of what Oersted did. He arranged so that well, I'll give you a top view. Okay, so he's got a battery and some rectangular wire like that. Okay, this is now the top view, and let's say so the current is going around, you know, in this direction. So the current through this piece would be up on the board. Now, if now let's look at this now from the side. So this is top. What he does is he rests this wire on little pivots here. So he raises it up off the table, and he's got it resting on little pivots. Okay. So it's a few inches up off the table, and you can see that now it can tip up and down, right? Okay. So he's just, it's like his rectangular wire is like, think of it as going on around the outside of my notebook here, but the notebook is free to pivot up and down. Okay, does everybody get the setup? Okay, so now what does he have to do? Well, let's say he brings a horseshoe magnet up now. A magnet in the shape of a horseshoe. Let's make this north and that south. Okay.
So it could have been anywhere that it didn't matter where the horseshoe magnet would be, on the side of the wire.
Well, he finds out it does matter, and the configuration that I've drawn here is the one that worked for him. So I'm going to give you another configuration in a minute, but now all right, let me figure out. Okay, let's say the current, which I told you was I last time, because all the other letters were used up. Now, when Oersted tries this, let me see. He finds that the wire, when he puts the horseshoe magnet around the wire this way, with the north pole on the inside and the south pole on the outside, and he turns on the current, the wire suddenly deflects, moves downward. What do you think happens when he flips the magnet around? And puts the north on the outside and the south on the inside. Now the wire kicks up when he turns on the current. Try.
Is the magnet like this or like this?
Oh, it's if I look at this this top view, now the magnetic, I've got a say in this case, I've got a south pole here and a north pole here. So it's
Horizontal.
the magnetic force is horizontal across the wire.
Okay.
See, now you wouldn't have, it's hard to guess this stuff, right? I mean, based on everything we've seen up to this point, we don't really have any way of predicting these discoveries of Oersted. Oersted himself was pretty surprised by this. And it was particularly surprising to people that, I mean, we saw in the first case, that first experiment, that the current would exert a force on the magnet that would deflect it perpendicular to the direction of the current. Well, we're seeing something similar here, right? When you put the magnetic force perpendicular to the current, that's when it works. So it's across the current, and in this case here that I've drawn, it will kick the wire up, and so this is up, and this is down.
Can you have two on the same wire, like one towards the top of the wire that's south-north and one towards the bottom that's north-south?
If you did both of these,
Yeah.
well then if the magnets were of equal strength and one of them was pushing up on the wire and one of them was pushing down, the wire wouldn't do anything, right? Ben.
So, say if this was the wire, and if you had the magnet here, it would go like this, or would everything just lift up?
Oh, if the wire were in this horizontal plane and you put the magnet like this, that, it turns out, would exert a force on the wire, but it wouldn't work in this experiment the way Oersted has it set up, because it would be trying to kick the wire to the side rather than up and down. See, the force is not in the direction of the force on the wire is not in the direction of the magnetic force. It's perpendicular. So if I had this kind of a case, the wire is only free to move up and down, and I've got the magnetic force in that vertical direction, then the wire won't do anything. I have to put the magnetic force perpendicular to the wire, but also perpendicular to the direction that the wire can move. See, it kicks it. Yeah, this is try to make this a little clearer. There's three directions here. Okay, there's the direction of the current. There's the direction of the magnetic force, and then there's the direction of the force on the wire, which is perpendicular to the other two directions. So we've got all three directions coming into play here. That if the current is in the vertical direction as I've drawn it on the board, and the magnetic force is in the horizontal plane of the board, then the force on the wire, in this case, will be out of the board. Troy.
Does anyone have any theory for why this
Well,
works?
I'm going to, all this is, I'm just introducing this topic now with Oersted. Oersted didn't know why this worked. And he was, at this point, just as confused about it as you are. But as we go on here, we'll learn the rules as to how these currents and magnets and forces work, and it'll start sinking in and seeming familiar to you, if not obvious. Troy.
Does electrodynamic current like attract the same way static electricity did, or not?
Oh, attracts between what?
Like objects would
So you mean will an electric current attract another electric current?
or like will this current like attract straw or something? Or
Oh, no. Electric currents don't attract objects that, I mean, they won't attract even a charged object. They won't attract an object that where there's no electric current in it. But we're going to see that there is you're on to something here that we're going to get to later in this class. Okay, so this is basically what Oersted discovered. That I mean, his first discovery was just that currents exert forces on wires. He knew enough Newtonian physics to suspect that currents through wires then must respond to forces from magnets. So if currents exert forces on magnets, magnets have to exert forces on currents. And he started working out the directions that these forces go in. Now that's about as far as Oersted got. And at this point, two physicists who were both better than Oersted sort of took over this subject. And we're going to spend the next few weeks talking about them. And the first one is a French physicist named André Ampère.
Are we
Sorry.
ever gonna do Ohm? Or
Oh yeah, I'm going to get to him. Didn't I have him listed after Ampere in the?
no, you actually have him listed before Oersted.
Oh really? Okay. Well, I'm doing it more in historical order here because Ohm actually didn't make his discoveries until after Oersted and Ampere. He's a few years after this. Oh, by the way, I should mention that I don't know whether I told you the year that Oersted made that first discovery, but it was 1819.
1819?
Yeah. And then as soon as Ampere hears about Oersted's discovery, he immediately realizes that this is huge news, and this is a major discovery connecting electricity and magnetism for the first time in history. So Ampere starts investigating it for himself. And the first thing he does is he repeats Oersted's first experiment, but he actually does it in a a better way than Oersted did it. So let's, Ampere's first experiment, he wants to investigate the effect of an electric current on a magnetic compass. Okay, so, but he wants to first get rid of the Earth's magnetic field. Because he wants to see just the effect of the electric current in the wire on the compass. Now, how do you do that? How do you get rid of the Earth's magnetic field? Daniel.
Aren't the is the Earth's magnetic field in the north-south direction?
Yeah.
So couldn't he put two large forces in the east-west direction and totally cancel it out?
Well, you got the right idea. He basically uses other magnets to cancel out the Earth's field. So if let's say the Earth's let's make this our directions here. So north is pointing up on the board. Now, what Ampere wants to do is take, say, a couple of big magnets. I don't know exactly how he did this, how he arranged his magnets, but it was probably something like what I'm drawing here. And if he puts magnets around like this, he can create a little space in the interior here. I mean, if his magnets are at the right distances and they're the right strengths, where he cancels out the Earth's magnetic field, where he creates the magnetic force from these magnets is the same magnitude as the Earth's magnetic force, but in the opposite direction. So it just balances it out.
Do they have to be a certain amount apart as far as width and length? Does this north and south have to be so far apart, and do the south and the south have to be so far apart? Or does it not matter at all?
Yeah, I mean, exactly where you place them will matter. I mean, I'm sure what he did was he has a magnetic compass in here, okay, and he just plays with his magnets until this thing just sort of spins around in any direction and doesn't point north, doesn't point preferentially in any direction anymore. So he's got a situation now where he knows that in the interior, there's no magnetic forces. Okay, so now he takes in this interior where he's canceled out the Earth's magnetic field, he puts a wire. And let's say the wire is coming out of the board. So current carrying wire out of board. Now, he can now go around with his magnetic compass and test exactly what direction the compass will point at various spots as he puts it around the wire. And he knows the magnetic force on that compass is just coming from this electric current. Okay, so if he puts the compass, I'll draw all the different locations here. What do you think what directions do you think he finds? Troy, you got a guess?
They're all gonna be like as like all perpendicular to the two along the sides will be perpendicular to where the wire is,
Oh, these will be
like up and down.
up and down.
Yeah.
Oh, okay. And how about these?
Side to side.
Yeah, you're right. In fact, what he finds is the compass needle points in this direction when you're on top. So it'll point toward the west when you're on top, and then down this side.
Is there an explanation of this?
Yeah. Well, what does it look like? I mean, I could even make it easier. Fill in a few more here. That's right.
If you reverse the current, would it go clockwise?
Exactly. Yeah, I was going to ask that question next. If instead of the current coming out of the board, the way I've drawn it, what if we just reversed the battery on this wire and had the current going into the board instead? Well, you would still get this circular pattern around the wire. It would just be in the opposite direction. It would be going clockwise instead of counterclockwise. But, I mean, the first important point to get here is that what a current through a wire does is it sets up these circular magnetic forces around it. And Ampere figured out how to summarize what this effect is. Ampere realized, well, if you take your right hand and you put your thumb in the direction of the current, your fingers will curl around in the direction of the magnetic force. Okay? So here, the way I've drawn it is just like that. So the thumb in the direction of the current, the fingers will always tell you how the circular magnetic force is directed. If you take and it works, of course, if you turn your hand around and your thumb is pointing into the board, in this case. So if I reverse the direction of the current in this wire, then your fingers curl around in the opposite direction, which is the direction then of the magnetic force.
But if you leave the current the same and then use your right hand, would it?
Oh, if you use the left hand,
Yeah.
you'll get exactly the wrong answer every time.
Like, so would it go like this?
So I recommend against that. That's why, actually, Ampere called this his right-hand rule, because the left hand doesn't work so well. Troy.
Is there any reason why you do like the same thing with screwdrivers to go in and out?
Oh, that's a question for an engineer, not a physicist. No, it's why are screws made the way they are rather than threaded the other way? Who knows? What? Yeah, I think it's because most people are right-handed, and it's easier to screw something in by turning it this way rather than turning it that way. Okay. So this is important. So remember, let me see, I should write down, everybody's got this diagram in their notes. It's worth writing down Ampere's right-hand rule. And we're going to call this right-hand rule number 1, which gives you a hint. More is coming.
I think he was towards the left.
And so we can state this, let me see, as let me see, point right thumb in direction of electric current then fingers curl in direction of circular magnetic force. See, now that's much better than what Oersted had, because Oersted just, remember when he did the experiment, he just looked at, when the compass was beneath the wire and when it was over the wire and when he reversed the current. But it's nice to have one simple rule like this that tells you, exactly what direction the magnetic force has to be in everywhere around the wire. Sorry.
But like when Oersted did the experiments, how would the rule work if the compass is here but the current's going above it?
Oh, well, let's go back to Oersted's case then. And now that we've got Ampere's principle and see what was going on there. At first, he had the wire draped over his magnetic compass, which was just laying on the table beneath it, right? And so and this was in the north direction, so the magnetic compass was pointing north just because of the Earth's field. Now, when he turns on his current, the magnetic compass is below, so what happens? So use the right-hand rule to figure out what has to happen. Okay, point your thumb in the direction of the current. What direction are your fingers pointing underneath the wire? In this direction, in the west direction. That's why Oersted saw the needle flip in that direction. So what happens now when Oersted took the magnetic compass and held it over the wire? You now put your thumb in the direction of the current over the wire. It's in the so below, above. It's going to deflect that way, right? According to the right-hand rule. So all of Oersted's results now just follow easily from this one simple rule that Ampere discovered. Okay? Okay. Everybody getting this? Now, Ampere has another idea. Okay, this is as far as I'm going to get in this class. Let me see. Actually, I've only got a few minutes left. Maybe that's not enough time to go into the next experiment. Oh, I think I mentioned last time that, or I mentioned it at some point not too long ago, that the electric force is actually very strong compared to gravity. Did I tell you? Okay. And that might strike you as strange because, it seems like we have to rub these glass tubes pretty hard in order to get a small little force, whereas gravity just keeps us anchored on the ground all the time. But you've probably never asked yourself this question, but why don't you sink right into the ground? I mean, the Earth is this huge object with enormous mass. Every bit of that mass in the Earth is pulling you down with that gravitational force. Right? What's stopping my feet from just going right into the ground right now?
The ground?
The ground is stopping me. But it turns out, Nick, you got an idea?
No.
Okay. Turns out that the force that's stopping me is electricity. I've got electricity in me, the ground's got electricity in it, and there's a repulsive force there. If the electricity in me gets too close to the electricity in the ground, that repulsive force keeps me from sinking into the ground. And that repulsive force, just exerted by this little bit of ground, is enough to overcome the entire gravitational force of the whole Earth. Okay, so that gives you an idea of how powerful the electric force is compared to gravity. Now, here's another way to look at it. If, let's say, JJ and Neve each had an imbalance in their electric fluids, and they were both about, they had 1% excess of electric fluid in them. So it wasn't, the positive and negative electricity wasn't balanced and exactly canceling out. They aren't neutral. They've each got a 1% excess. Well, there would be enough force between them right now, enough repulsive force to lift the entire weight of the Earth. So that's how powerful electricity is compared to gravity. And eventually, people are going to figure out how to harness at least a small fraction of that force and run all of modern technology on that power. And the key to that is figuring out these laws of what electricity is like when it moves. So more about that this afternoon.